Okay, welcome Year 10 students to this vodcast on quadratic applications. Okay guys, the name of the game is applying your technique of quadratic equation solving to worded problems. So we're going to look at 4 examples that should highlight the sort of techniques and thinking involved. So here's one particular question. It's kind of nice for us. The unknown is defined for us. That always makes things easy. And in fact, this also leads us through finding out the component parts that are involved in setting up the equation. Okay, let's have a look. So a square lawn is surrounded by a concrete path 2 meters wide. If the lawn has side length of x meters, find in terms of x the area of the lawn. Well, that's a bit of a no-brainer. X times x is equal to x squared. Now the area of the concrete path, of course, that's this area over here. This is what I need to describe in terms of x. Okay, and that's not such a no-brainer. So let's explore how you would go about modeling the area of the concrete path. Well, we know the path is 2 meters wide. So with that in mind, what we've got is an area consisting, well, we've got a path plus lawn that will be not just x meters wide, but x plus 4 meters wide. And that's the same on both sides. Okay, x plus 4. All right, nice. So what does that mean about the combined area of path plus lawn? It'll be x plus 4 all squared. But we're not interested in the area of path plus lawn, just the area of the concrete path. So from it, we need to subtract the area of the lawn. Okay, so let's go and get an expression for the area of the concrete path. Expanding brackets, x squared plus 8x plus 16, take x squared, leaves us, of course, with the x squareds will cancel, 8x plus 16. So there's an expression for the area of the concrete path. Now, how do we match the two? Okay, this is the equation part. The area of the concrete path, which we're given this expression for, is equal to 1 1/4 times that of the lawn. Actually, I should have, let me just get a different color. That might, okay. Let me just get purple. 1 1/4 times that of the lawn. So this facilitates setting up the equation as follows. 8x plus 16, the area of the path. We're going to set that equal to 1 1/4. Let's change that mixed number to an improper fraction. 5 on 4 lots of x squared. Why x squared? Because that's the area of the lawn. There it is. That's the quadratic equation that we'll need to solve now. Okay, so let's go through the routine. Let's move all the terms to one side of the equation. Or in fact, let's just remove the fraction component, multiply all terms by 4 first. Always like to do that. 5x squared is equal to 4 times 8 is 32x. 4 times 16 is 64, and moving those terms across to the same side of the equation, 5x squared minus 32x minus 64 equals 0. Okay, so there's our quadratic equation. It's a non-monic situation, so what I would do is use the AC approach, which is 5 times negative 64, 10 times 64 is 640, divided by 2 is 320. Okay, so we're looking for factors of 320 that sum to negative 32. Okay, you've got 32 and 10, you've got 16 and 20, you've got 40 and 8. Aha, so positive, well, it's got to sum to negative 32. So what I'm going to do is now rewrite the equation. 5x squared minus 40x plus 8x minus 64 Doing a grouping 2 and 2, 5x, and that's x minus 8, plus 8, x minus 8 equals 0, x minus 8, 5x plus 8 equals 0. Now solving for x is equal to 8, or x is equal to minus 8 on 5. Now we can reject it, because x must be clearly a positive value, being a measurement, and then we arrive at our particular value of x that satisfies the given criteria. Now find x is the question. Obviously x is in meters, so all good. Okay guys, here's another question. In a right angle triangle, the hypotenuse is 8 centimeter longer than the shorter side, and the third side of the triangle is 7 centimeters longer than the shorter side. Find the length of the shorter side. Okay, now typically, and it's sort of no different in this particular case, the quantity we need to find, which in this case is a length of a right angle triangle that happens to be the shorter side, is how we define our unknown. So x is length of shorter side. Okay, the next thing is to create a diagram. Obviously we're dealing with a right angle triangle, and define all side lengths in terms of x. So here's our shorter side length. Here's our hypotenuse, which is 8 centimeters longer than the shorter side length. By the way, we should set the units nice and clearly. The length of the shorter side is x centimeters, and here's the other non-hypotenuse side length of the right angle triangle. All right, we need to form an equation. What's the one very famous rule that links the side lengths in a right angle triangle? That's right, it's Pythagoras' theorem. C squared equals a squared plus b squared. So with regards to Pythagoras' theorem, we need to make our replacements. There's x plus 8 all squared will be equal to x plus 7 all squared plus x squared. We should find that we'll get an equation that emerges out of this situation when we expand the brackets and collect like terms that we can solve and find out what is the value of x that satisfies this situation. So perfect square expansion, x squared plus 16x plus 64 is equal to x squared plus 14x plus 49 plus x squared. Okay, we can see two of the x squareds will kill each other off anyway, so we are going to be dealing with a quadratic equation. Let's move all the terms on the left to the right hand side of the equation. So we've got x squared, we've got 14x take away 16x leaves us with negative 2x, and then we've got 49 take away 64 leaving us with negative 15 equals 0. So 15 plus 49 is 64. This looks like a nice easy mnemonic equation to solve. Factors of 15, 5 and 3, negative 5, positive 3, leading to my two values of x. X is equal to 5 or negative 3, but of course I reject the negative because again it's a situation where my values must be positive. So what is x? The value, the shortest side length in this right angle triangle is indeed 5. In fact, let's just refer back to this situation. We're dealing with a triangle of side lengths 5, 12 and 13. And of course that's one of our famous triads, Pythagorean triads. Alright folks, here's another problem to have a look at. It's more of a modelling question, so it's another nice application of quadratics. In this case we're modelling the height in meters that a rocket has risen t seconds after being launched from sea level. and it's given by that particular equation. So let me just focus in on it. There it is. There's our modelled equation. H is in meters, T is in seconds. Now, if you notice, unusual about this question, it's got a third parameter, a third unknown or pronumeral, and that's simply representing the launch velocity. Now, that's a little bit weird, but if you have a look at the questions, it makes perfect sense. So firstly, we need to calculate the height that this rocket will reach above sea level, the point of projection, 4 seconds after being launched, if it has a launch velocity of 115 meters per second. So all we have to do, obviously, in this case, is replace u with 115 in the equation. Okay, so then that's the equation matching the given situation. And we have to work out the height it reaches after 4 seconds. So find h when t equals 4. So that's really all it is. So h, we've got to find h. So let's just write out the full equation. T minus 4.9 t squared. And we need to work out h when t is equal to 4. So 115 times by 4 minus 4.9 times 4 squared, which is 16. Well, we can do this by hand. Take out 4 as a common factor, 115 minus 4.9 times 4. All right, that's 4 times 115 minus 19.6. 115 minus 20 is 95 plus 0.4. So it's 4 times 95.4. 4 times 95, 2 times 95, 190, 380. 380 plus 1.6 is 381.6. Now, of course, if we had access to a CAS, we wouldn't go to that trouble. We'd actually go along something like this. Let me just get rid of that. Okay, we'd sub it into our CAS. We'd define our function using a U value of 115. And that we've got the ability to actually, with that function notation, we could actually just replace our independent variable by 4 and immediately get our answer. Very nice indeed, isn't it? Okay, what about the second one? Okay, we've got a launch velocity can be a maximum of 500 meters per second. Of course, that's just another U value, isn't it? There it is. This time U is 500. Calculate the longest possible time of flight to the nearest second. Okay, so what's this about? The longest possible time of flight obviously must occur when the launch velocity is at its maximum. So in other words, we're going to be working with this equation. H is equal to 500. Out goes U, in comes 500. So, all right, so that's modeling the height that the rocket reaches above sea level, but above the point of projection, and with a maximum launch speed. So the longest possible time of flight, in fact, the question's a little bit lacking in detail, because what we're going to do is assume that the point of projection at sea level, when it returns to sea level, it's no longer in flight. But of course, we could be launching it at a point where there are places on Earth that are below sea level, and it could continue to be in flight. So there's a few details a bit lacking in this question, but what we're going to assume is that it's been launched from sea level, and when it returns to sea level, it ceases to be in flight. So how do we get a solution to this particular equation? What do we need to do? If you were guessing, well, not guessing, if you were working along the assumption that what we need to do is find t when h is equal to 0. So obviously t equals 0 is 1 because it starts at the at sea level. But if we solve this equation, 0 is equal to 500t minus 4.9t squared, which clearly we can take out t as a common factor. 500 minus 4.9t and solve, then we're going to get our answer. And clearly from that, from solving that equation, we get the value of t to be 500 divided by 4.9. That would have to, we can't leave fractions in that way. So obviously multiplying top and bottom by 10 is one way to get around it. And of course we could use our CAS as well. So let me just get rid of the pen. And what would I do? That's how you might get it done with CAS. So I've redefined the function. I've used g. I've replaced u with 500, and I've gone to solve it for x. Obviously, x equals 0 is one solution, which makes sense mathematically as well as practically because it's been launched from sea level, and it takes 102. Wow, that's ridiculous. It takes 102 seconds for it to return to Earth. Oh, well, it is a rocket after all. Okay. And please take note, we've got to read the question, make sure we're answering it as required to the nearest second. So our answer will be the time we'd write it to the nearest second is 102 seconds. Okay, there we go. Now, while I'm on CAS, I might just show you an alternative way this could be done. And that would be this kind of definition, a little bit more advanced use of CAS. To find f of x, what we're going to do is the one definition, and we're going to use u times x minus 4.9 times x squared. And so you can have a look what I'm doing over here. I'm asking the CAS to work out the value of the function when x is equal to 4, when t equals 4, but on the condition that u equals 115. Of course, we get the same answer as we did before, 381.6 meters. And in the second one, with the one defined function, I'm asking to solve the function for 0 to find out the values of x or the values of t when the height is 0, when it's returned to sea level, but on the condition that u this time is 500. So that's just an alternative way you can use your CAS, just out of interest. All right, so that's a modeling application of quadratics. All right, guys, here's the final application question for quadratics. We've got a sheet of cardboard, 24 centimeters long, 17 centimeters wide. Okay, let's just assume that's a rectangle. Has squares of side length x centimeters cut from each corner. So fixed dimension squares cut from each corner, and then it is folded to form an open box with a base area of 228 centimeters squared. Find the dimensions of the cardboard box. Okay, now obviously in this particular modeling situation, x is given to us, so the key really is all in the diagram and understanding how a box is formed from a rectangular piece with squares cut out at each corner. This becomes quite a common thing that you'll see. You'll see this sort of question reappear several times, particularly in the calculus unit and the polynomial unit you'll be doing next year. But let's begin with a diagram. Okay, obviously not to scale. There's some rectangle drawn. Okay, now what does it mean to have squares of side length x cut from each corner? Well, it would look like this. Okay, so let me just annotate it. So each square that you see no longer part of the original rectangle is of equal length, and that length is x centimeters. Okay, now I've also got on that diagram some dotted lines. That's where the folding would occur. Okay, so when you do fold it, you'll get that lovely open box look. So there's each side length looking like that. Okay, so the height of the box will be x, and then you'll have a base length, a rectangular base. Let me just highlight the rectangular base. So there's my rectangular base, and that would relate to this area here in my fold. So hopefully that's nice and clear for you. Okay, so there it is. Okay, but how to describe the length and width of the base of the box? Okay, and obviously the base area is 228 centimeters, so length by width will end up being 228. So this really comes down to what's the length and width of that green rectangle that's shaded. Okay, so hopefully some of you are onto it. We started out with a length of 24 centimeters, to which 2 lots of X has been removed, an X on this side and an X on that side. So that length, therefore, is 24 less 2x. Now, if we go to the width, we started with 17 centimeters, but of course, 2x has also been removed from that. So that's the width of the box is 17 less 2x. All right, great. Now, what we're told is the area of this is 228 centimeters squared. So what shape is it? It's a rectangle. Formula for area of a rectangle, length by width. So we can begin to set up our rule. 24 less 2x, length times by width is equal to 228. That's the equation I need to solve. Okay, so all right, so we can go in and do it by hand. Expanding brackets would be 4x squared. Okay, then we've got 2 times 24 minus 2 times 24 minus 2 times 17, so 48. 48 plus 34 is 82, so we've got minus 82x, and then we've got 24 times 17, so 17 times 20 is 340, 17 times 4 is 68, 340 plus 68 is 408, plus 408 equals 228. Subtracting x squared minus 28x plus 180. 408 less 228 is 180 is equal to 0. Okay, and then of course dividing by 2. 2x squared minus 41x plus 90. We're getting closer and closer. All right, the usual routine for solving equations. We're looking factors of 2 times 80 that sum to 41. Okay, a bit of a challenge. I know that 9 times 10 won't get us there. So I know, what is that, 16 and 5? 16 and 5, no, sorry, 18 and 5. So 2 times 18, that would be it. Okay, so it'd be x minus, sorry, let's go 2x and x. So that would have to be minus 18, and of course 5 equals 0, and that leads us to our solution of x is equal to 2.5 or 18. Of course, there's a lot of calculation involved in all of that. If you've got CAS allowed, what would you do? You just whack it into your calculator, just like that. No need to simplify, move things around, solve. Length by width equals 228 for x, and there we have it. We've got our 2 possible values for x, 18 and 2.5. Now, one of them is just not making sense physically, is it? Okay, so if I start with a side width of, actually let me just change my color, a side width of 17 and 24, can I really take out 2 chunks of 18 from it? I can't. Okay, and similarly, I can't even take out 2 chunks of 18 from 24 either. So x equals 18 is rejected as a possible solution. Only x equals 2.5 or 5 on 2 is feasible in this particular situation. The question is though, what are the dimensions of the box? So the dimensions are 2.5. Let's just write it as 2.5 is the height of the box. There it is, there's 2.5. The width of the box is 17 minus 2 lots of x, so 17 minus 5, which is 12. And the length of the box is 24 minus 2 lots of x, which is 19. So these are the dimensions of the box. That's height by width by length. Okay, all in centimeters. Okay, and there we go. Okay, guys, so that's a wrap for this session. We've covered a range of different quadratics problems. Hopefully that will help you in your endeavors and your journey through applying quadratics to real life problems. That's bye for now.